we've been talking about migratory displacement reactions. So these are reactions that, in theory, they could go through a carbocation intermediate, a carbenium ion intermediate, but they don't go through carbenium ions. They don't go through some sort of an intermediate where there's only 6 electrons on a second row atom. Instead, what we're seeing over and over again is that we're going to push out the leaving groups using neighboring bonds. Right? And those bonds need to be antiparaplanar to be aligned with the sigma star orbital of the leaving group. So we're going to be looking for this pattern of bond alignment in order to make these processes facile. We're going to talk about a rearrangement that's used in the semiconductor industry to produce microchips. So if you've ever wondered how they produce microchips, they have these things called masks, and they shine light through them onto silicon wafers. You could just draw a mask with a magic marker. They used to take a photograph of a big board, and then it would appear on the film as this miniaturized version. And when you shine light through that mask, wherever it hits, it can do photochemistry and create patterns, whatever pattern you want it to create. So if you smear this goopy resin, for example, Novolac resin, that's mixed in with this photochemical reactant, you can create patterns. That's how they create the chips that run your phones, that run everything. Organic chemistry is essential for modern photolithography and modern chip production. I'm going to show you, maybe this is, I'm not sure if they still use this particular type of photolithographic reagent, but there's a class of functional groups called alpha diazocarbonyls. This position right here is the alpha position. Unfortunately, that particular resonance structure, it's the common one, but it's not the one that is most helpful to you in understanding what's going on in this very interesting rearrangement called the Wolf rearrangement. I'm going to draw a resonance structure of this that really helps you to see what's going on. And I'm going to take these lone pairs here and push down and then move these electrons to make this look like an enolate. This is the resonance structure that's going to be very helpful in terms of understanding what's going on in this migratory displacement process. So nothing happens at room temperature. These alpha diazocarbonyl compounds are stable. When I draw this other resonance structure, I hope you can see, hey, wow, look at that. There's a nitrogen leaving group, nitrogen gas. That's ready to act as a leaving group, especially if we heat this thing up. And so let me circle this charge here on the oxygen because it looks like a bond. I don't want that to look like a bond. So there's a negative charge on the oxygen. This is an enolate. The lone pairs on this oxygen, you can't change this. The lone pairs on this oxygen are anti-paraplanar to this R carbon bond. It's going to weaken that R carbon bond. It's going to make this bond here more nucleophilic. Longer, weaker, more nucleophilic. And that makes it possible when you heat this system up. If you heat this system, it'll migrate over. The R group will move over and push out that nitrogen gas leaving group. That arrangement of weakening the bond, just like we saw in the Pinacol reaction, that arrangement of lone pairs weakening a bond, and then the R group migrates over and pushes out the leaving group, is a common theme. Now, you get this funky, it's kind of a little bit strange if you've never seen a ketene before, but it's important to recognize that you started off with the R group over on the carbonyl carbon, but in the end, the R group has migrated over by one atom, has migrated over to the neighbor. This functional group is called a ketene. It is particularly reactive because it doesn't like, that middle carbon doesn't like being sp hybridized. And you could put all kinds of nucleophiles in with these, and they will want to attack that ketene group. That's supposed to be a lone pair on a nucleophile, but it's not well drawn. There we go. Nucleophile with lone pair, alcohols, amines, hydroxide if you had it in there. So let's take a look at this process of photolithography. You spread some goopy stuff on top of a silicon wafer. That's called photoresist. And then you shine light through a mask, and wherever the light hits, you do photochemistry. And the reagent they're using is called, the class of reagents is called a diazonaphthoquinone. That's this thing. This whole thing here is called I guess you could call that a naphthoquinone. It would be a quinone if this was a carbonyl. But this is a diazonaphthoquinone. It's got an extra solubilizing group. That's not important for the arrow pushing mechanism. So to understand what's going on here, let's just redraw that cool resonance structure that I mentioned just a second ago. Let's redraw that in a useful resonance structure where I can see that there's a bond antiparaplanar to nitrogen gas as a leaving group. Whoa, 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 I don't want that C double bond O. I want this enolate resonance structure. There's that O minus. Here's that nitrogen gas ready to act as a leaving group, that diazonium group. So, and again, this lone pair over here on the oxygen is bending over and weakening this CC bond that is antiparaplanar to that. It's weakening this bond. This bond is now more nucleophilic. It's weaker. It's easier for that to migrate. And in this case, for photolithography, you don't use heat. If you can get this system to absorb a photon of light, once you absorb a photon of light, boy, that's a ton of energy. It now has a bunch of energy, and so it's very easy for this bond over here, this weakened carbon-carbon bond, to migrate over to the neighboring carbon and push out nitrogen gas as a leaving group. So you get this ketene intermediate, and so then they come along with sodium hydroxide solution, and they wash the surface away. And wherever you had these ketenes, those ketenes react with the sodium hydroxide solution. I'm not going to show you all the steps in this arrow pushing mechanism here, but you convert that ketene into a water-soluble carboxylate anion. Let me just highlight that negative charge. That now makes all the goopy polymer next to it water-soluble. It just washes it away like a detergent. It just washes away that goopy polymer and leaves behind these patterns that they can then use to oxidize the silicon surface or fill it in with other stuff. That Wolff rearrangement, it's bond alignment that allows that to occur, and you've got this incredible leaving group sitting there waiting to nitrogen gas, ready to leave once you heat it or hit it with a photon of light. Let's take a look at another, it's a very similar looking reaction to the Wolff reaction, but all we're going to do is we're just going to replace carbon with nitrogen and it'll be the same thing. But we're going to make a slightly different functional group here called an acyl azide. So if you take sodium azide, I'll go ahead and draw out the Lewis structure for the azide anion, just in case it's not obvious. Here's the Lewis structure for azide anion, readily available salt, sodium azide. It's got 3 formal charges in there, but the ends of this are nucleophilic, either end of that. There's lone pairs, and they can substitute that acyl chloride. I'm not going to draw the 2-step mechanism for substituting the acyl chloride. You attack the carbonyl with the azide anion, and then in a second step, you push out the chloride. And that will leave you with a functional group that is pretty unstable. You don't really want to isolate these types of species. They tend to be explosive. You could for a short period of time or in small amounts, but you wouldn't want to have a bucket of this sitting around. It would be potentially sensitive. Now, I'm going to draw this particular resonance structure, but again, this is not really the resonance structure, I think, that is the most helpful to you. In order to help us understand what's going on here, let's go ahead and draw another resonance structure like we did for that Wolff rearrangement. I'm going to use these lone pairs here on this end nitrogen, and I'll push down here so you can see that I've got the equivalent of a diazonium leaving group. Nitrogen gas is a leaving group. So let me keep pushing these electrons into the carbonyl. I'm just drawing a resonance structure to help us understand what's going on here. And so in that resonance structure, I've got an enolate. I wish I'd drawn that RR bond longer, but I didn't do that. So now I've got a nitrogen atom right here, and our old friend nitrogen gas as a leaving group, just poised and waiting. Let me circle that minus so it doesn't look like a bond. So this should look just like that other system. So you heat these. If you want it to occur quickly and under your control instead of exploding, you heat these usually 80 degrees, 90, 100 degrees, and you'll get a smooth rearrangement. This is called a courteous rearrangement. Acyl azides undergo courteous rearrangements. Let's go ahead and draw the arrow pushing for that. It's just like that Wolff rearrangement. I'm going to use the lone pairs on oxygen. They're pushing down, and they're trying to push out that R group. They can't, but they're lengthening it and weakening it. This bond is long. It's more nucleophilic because it's being weakened, and that makes that bond particularly able to migrate over to the nitrogen and push out that nitrogen gas. So you lose nitrogen gas. You can see the nitrogen gas bubbling out of your reactions when you heat these things up. And the functional group that you generate now has this nitrogen R bond. The R is now attached to nitrogen instead of the carbon. And this functional group is called an isocyanate. Isocyanates are also electrophilic on the carbonyl. It's very easy for nucleophiles to attack these carbonyls. Let's go ahead and draw out the mechanism. It's not really related. The reaction of isocyanates is not really related to migratory displacements. But when we cover organic chemistry here at UC Irvine using this Gorzinski-Smith textbook, we don't cover this class of molecule called cumulines. When you have these two heteroatoms on a carbon or like a ketene, those are called cumulines. When you have two double bonds on the same second row atom, those are called cumulines. So let's go ahead and take a look at what would happen if you treated an isocyanate with an amine nucleophile. You could also use an oxygen alcohol nucleophile in these cases. You usually have a catalytic base present. So if we go ahead and draw the arrow pushing here, as I come over here and I attack that carbonyl, I've got two choices. I can push the electrons to the oxygen. I can push the electrons to the nitrogen. Won't matter. That'll just give me two resonance structures of the same thing. You push the electrons to either oxygen or nitrogen, depending on how you want to do it. This case, I'm going to push the electrons over here I'll break the CO double bond and give the electrons to oxygen. There we go. And let me go ahead and draw out that next intermediate. In this case, we're reacting with phenyl isocyanate. My gosh, that stuff is a powerful lacrimator. Makes you cry. I remember somebody once was washing a piece of glassware when I was working in an undergraduate lab that had some phenyl isocyanate on it. And it's like tear gas. I mean, it cleared the lab. We were like, oh. We had to run in until we could finally figure out which sink had the stuff in it and wash it down the drain. Yeah, isocyanates are used to make polymer foams for insulation and stuff like that. So let me go ahead and draw out this. This is a methyl group in this case. And so now, to get to our final structure, we just need to pull a proton off the N plus and then put it back on the other end. So that's not all that dramatic here. Let me just go ahead and, we're in basic conditions because there's an amine in there. Let me go ahead and draw. It's not really all that exciting. I'm going to pull a proton off the amine, off the ammonium group here, and then I'm going to put it back on the other nitrogen. So now I've regenerated this conjugate acid from my base. Oh, that's a lousy looking plus charge. Let me see if I can fix that. When I get down to the bottom of my iPad screen, I'm trying not to shift my page up like, I'm trying not to shift my page up and do weird stuff. So still struggling to learn how to write on one of these iPads. Okay, let's go ahead and show that we're just putting a proton over here on this other nitrogen. And that's how you get to this functional group over here where there's two nitrogen groups attached to a carbonyl. That's called a urea when you have two nitrogens on a carbonyl. An amide has one nitrogen. A urea has two nitrogens, common functional group, common in pharmaceuticals, common in nature, in biochemistry. It's a pretty common functional group. Okay, so this Curtius rearrangement gives you isocyanates. It's kind of like the Wolff rearrangement gives you a ketene. So Curtius rearrangement. And there's that marvelous arrangement of weakened bonds and good leaving groups and anti-periplanar relationships that makes that possible and allows that to occur. Let's take a look at essentially the same reaction, kind of the same reaction. And this is, it's actually two different reaction recipes for achieving the same thing here. So these are called the Hoffman and Curtius rearrangements. Let's go ahead and take a look at what's going on with that and how we get to an intermediate that looks a lot like that Curtius rearrangement. So how do you do this? So you can see the reaction recipe here is you take sodium hydroxide, you take base and Br2. You could also do this with sodium hydroxide and Cl2, better known as bleach, like the bottle of bleach you use on your laundry. That would probably work here and give you the same kinds of results if this is what you wanted to do. So let's go ahead and take a look at the key intermediate here. I'll go ahead and draw the the mechanism, well, I'll draw some of the mechanism. I'm not going to draw the initial stage here. The first two steps are I don't think are interesting enough for us to show because it'll make the mechanism too long. But you've got basic conditions here. And under the basic conditions, we're going to deprotonate this rather acidic NH2. That's not like a regular amine NH2. That's an amide NH2. A little bit less acidic than water, but not hard to pull that off, right? If you want 10% of this to be deprotonated, you just dump in sodium hydroxide, and there's amide anion floating around, and that then attacks the Br2 and puts a nitrogen bromine bond on there. I'm not going to show that whole thing. Whoops, I'm not going to show that whole mechanism because I don't think it's that inspiring to us right now. Let me go ahead and draw this out. So in two steps, we would have an N-bromoamide. Let me draw that long bond there. You know that's going to do something. You got a bond between two electronegative atoms. That bond is weak. Easy to substitute and push out something when you got that weak kind of a bond there. Look how long it is. It's ready to do something. But you need the base here. You need the base before it does anything. And what the base does is the base will come along. In this case, it's the hydroxide. You can draw the letter B as a symbol here. It won't matter. I don't know why I drew the hydroxide out. You could just write B for arrow pushing. And so we're going to deprotonate this, and I'm going to push the electrons up into the carbonyl so it looks kind of like an enolate. It's just a deprotonated amide. So when I draw this next intermediate out, it'll have that O minus there. It'll have this bond, this double bond. It'll have that bromine atom there. Look at that bond. Boy. Now, it's not nitrogen gas, but it's a pretty good leaving group. Right? It's a pretty good leaving group. And it's not nitrogen gas, but it's a bond between two electronegative atoms. So easy to break that bond. And we've got this same great rearrangement here of groups. We've got the lone pairs on this oxygen that are bending over. Those lone pairs on that oxygen are always overlapping with the sigma star orbital of this CC bond. That sigma star orbital is back here. The sigma star orbital for this bond is on the back end and overlapping with that lone pair. You can't stop that overlap. It's there all the time. And so these reactions at room temperature with that weak nitrogen bromine bond at room temperature, this could migrate over and break that weak bond and push out the leaving group. And so the product that you get out of this process should look just like that Curtius rearrangement. Maybe I shouldn't call it a product. In this case, I would call it a reactive intermediate. That I don't think they try to isolate this. I'm showing you a particular version of this reaction. And in this version of the reaction, they were trying to make a tertiary carbon-nitrogen bond. Now, it's not easy to do SN2 at tertiary centers, so this was a very useful transformation. If you want to make a tertiary carbon-nitrogen bond, you start with this readily available carboxylic acid derivative, which you could alkylate alpha to carbonyls, doing alkylation chemistry, and then you do this Hoffman rearrangement. And you get this carbon-nitrogen bond where you used to have a carbon-carbon bond. And then maybe the transformation doesn't seem so valuable to you, but the next thing they do is they hydrolyze off completely this isocyanate. You could use acid or base for this. They probably just use sodium hydroxide in order to do this. And this is the way you synthesize a molecule called phentermine. It looks very similar, if you just move the nitrogen over, it looks very similar to amphetamine. They used to sell back in the 90s. Every single billboard, every magazine had advertisements for the fen-phen diet pill. Ooh, take the fen-phen diet pill. Half of the fen-phen diet pill was an amphetamine derivative called fenfluramine. You just take amphetamine, put some fluorines on there, and there you go. You got a fluorinated amphetamine derivative. The other half was phentermine, which is also kind of similar in structure to an M. So they were basically selling a lot of these fen-phen diet pills with amphetamine type analogs in there, which amps you up, I guess, gets you. A lot of those types of compounds cause heart problems. They activate the human etheragogo gene receptor thing or something like that. It's a common problem with drugs that they always screen for nowadays. Yeah, so that got pulled from the market. Okay, so, changing carbon-carbon bonds to carbon-nitrogen bonds using this Hoffman rearrangement is pretty useful. Okay, this group is migrating over, this R group is migrating over in this step. And so if that R group had a stereogenic center, was a stereogenic center, you would preserve that during the migration. You wouldn't change the dashed or wedged bonds attached to R during the migration step. So the chirality of the migrating groups in Curtius rearrangements and these Hoffman rearrangements are preserved. This is not a stereogenic center, but if you had one methyl and one ethyl, you would have preserved the chirality there during that rearrangement process. Just for these ones. For the migratory displacements, you preserve the rearrangement, or the stereochemistry. Okay, so the last one, there's a lot of these. We don't have time to talk about all of these migratory displacements, but I'm giving you a selection here of some of the common ones. So another common migratory displacement process is called the Beckmann rearrangement. It's a little bit different because it's going to generate a triple bond instead of a double bond. So typically, a Beckmann rearrangement has these features associated with it. You'll have some C double bond N, and then you'll have a leaving group on there. Now, hydroxide is not a great leaving group, so they have to do something here to turn the hydroxide into a good leaving group. 100 years ago, they would just dump in acid. That's what they did with everything 100 years ago. We're a little bit more gentle nowadays, but if you just protonated that, you could turn that into a decent leaving group. So how would that look, right? We just take some sort of an acidic species. I'll just depict that as HA, and you can just protonate that. Certainly plausible. Now, you might be saying, well, Dave, isn't nitrogen more basic? That's exactly right. Yeah, you would protonate nitrogen more frequently than the OH, but you're not going to be able to explain this rearrangement by protonating the nitrogen. So once you protonate the nitrogen and can't get anywhere, take the proton back off and think about somewhere to put it on there. It is protonating on nitrogen, but you can't explain the products by leaving the proton on there. So take that proton right back off, because that's what's happening in solution. And now we've got this leaving group that is just poised here on our oxime. This is called an oxime derivative. Those are so easy to make from ketones. You just add hydroxylamine. So now we've got this nitrogen. We've got this leaving group. You can tell it's going to leave somehow. And I've got two of these groups on here. And so now what's going to happen is we're going to migrate over and push out that leaving group. We're going to migrate over and push out that leaving group. So this is going to, maybe this will, I don't know if this will freak you out, but there's a nitrogen, we're going to end up generating a nitrogen-carbon bond here, and we're going to end up generating a triple bond. Actually, this should not freak you out because we've seen this intermediate before, now that I think about it. We have seen this intermediate. This shouldn't freak you out. This is the same electrophilic species that we got when we did this thing called a Ritter reaction. So I think on one of our first problem sets, we had nitriles attacking carbocations to make this nitrillium species. This is a nitrillium ion. I've given you the name up here. So you also get these types of nitrillium species when nitriles attack carbocations. You can't make a phenyl carbocation. But that triple bond with N+ wants to be attacked on carbon so you can give the electrons to nitrogen. And so if you're in the presence of water, the water, of course, would attack here. This is done in the presence of water. I'll go ahead and draw out the first step, but there's a lot of proton transfers in this mechanism that I'm not ready to go through. You're going to have to take a proton off of maybe I should have made that attack the top because it would look more like the product. But that's the species you get after the migration, and that would undergo a hydrolysis reaction with water. So you'd add water in there. I remember now, I think in our problem set there was no water, and so you used the acetic acid carbonyl to attack, and you eventually got to the right product. Yeah. Sorry. I didn't finish the mechanism. So we need to use one more we need to use one more bond forming event here. Let me go ahead and use this and push that back down. That's where the triple bond comes from. You need to use that nitrogen lone pair in order to generate the triple bond. If you did it the way I drew the arrow pushing, let's go ahead and draw the arrow pushing the way I did it. Boy, I'm making things, let me take that last arrow away. Let me do it like this. The arrow pushing that I showed you, yeah, great question. So where does that triple bond come from? My arrow pushing should give you this. Yeah, my mechanism wasn't complete yet. My arrow pushing would give you this. It would give you C here attached to ethyl and a carbenium ion, and then I would draw the resonance structure like this. Or you could have used that lone pair in the very beginning of this rearrangement. So that gives you this nitrillium ion, and that's a resonance structure. These are both resonance structures of each other to give you the nitrillium ion. So nitrillium ions aren't stable. They want to be attacked. They will be attacked by something no matter what. So here's an example down below where instead of just throwing in acid, they're using slightly gentler conditions by turning that OH group into a sulfonate leaving group, a tosylate leaving group. So the conditions that they're using here is that they're using tosyl chloride in pyridine. There's no way to go through a sulfene type mechanism. This is a very traditional type of mechanism. I'm not going to draw out the mechanism for that arrow pushing step, but you end up generating an oxime. This N with the OH is called an oxime, but this has a tosylate leaving group. So you should know that that's a leaving group. I'm just going to write R and AR here because I've run out of room at the bottom of my page. And this is going to undergo this Beckmann rearrangement. They're heating it just a little bit. Kind of surprised that they don't have to heat this more, but it occurs. It's with just a little bit of gentle heating. And so now we're going to go ahead and I'll try to draw all this occurring in one step. I'll push down with these electrons here, and then we're going to migrate over and push out the leaving group. And that's going to lead us directly to this ring expanded product. The nitrogen that the carbon atom that used to be attached to this imine carbon is now going to be attached over to that nitrogen. And so where we had a 7-membered ring before, who would have thought that this was possible? We're now going to have this 8-membered ring intermediate with a triple bond in it. Boy, that looks crazy. Who would have thought? You wouldn't have known that you could have an 8-membered ring. I wish I'd drawn that in black just because that matches the rest of the structures. Who would have known that you could have had a triple bond in an 8-membered ring or any kind of a ring? Doesn't that look strange to you? Right? A stop sign doesn't have 180-degree bond angles inside the stop sign. But this definitely wants to react. Initially, they do this workup in a second step. So it's going to react, and in the meantime, while it's waiting for you to add in water, that chloride that's been floating around from your tosyl chloride is going to add in, and it's going to give you this chloroaminium species, so where this is equal to chloride. And those are reactive. Those will react with water. So if you have water present, the water will come in here and attack during the workup. You come in later in the afternoon, you add in water, and that's going to hydrolyze that. Let me take that out because that was probably adding through acid catalysis, and I don't want to draw out the whole mechanism there. Now, just so we're clear here, don't get comfortable drawing triple bonds in small to medium-sized rings. When they tried to do this by starting off with a 6-membered ring, so notice how they started off with a 7-membered ring. They get a pretty decent yield off of that. When they tried to do this by starting with a 6 and expanding it to 7, they gave low yield. It gave low yield in that process because the 7-membered ring just can't handle the triple bond. You just went away. So don't get comfortable with triple bonds certainly not in 6, not even in 7. 8 was about the smallest ring size they could get that nitrillium intermediate to work well in. And I respect them for trying all the ring sizes just to see where the system broke down. All right, so that's the Beckmann rearrangement. Now, I'm now remembering there was another question about the exam, about what do we cover. And I posted the answer key for last Friday's problem set that we did during discussion section. That's all available for study. and I can't remember, does the exam cover stuff through that last problem set, or does it stop the week before? Okay, well, we'll try to mention something on there. I don't recall putting stuff from last week on there, but maybe if we did, like maybe silicon, or I don't know, what is the, I guess we covered that before last week too. I don't know, I don't even remember what's on the exam. Right? Carbocations, like I'm sure there's going to be bonds donating into carbenium ions or something. Okay. Boy, migratory displacements, they look so fancy and so hard to figure out, but you know, once you've seen one migratory displacement with a weakened bond migrating, it starts to get old, right? You could now go off and invent your own. It's like if I just arrange some leaving group anti to some bond and I weaken the bond, maybe you can have your name on a rearrangement. You can't, because they've all been done. Every variation, I say that maybe that's not true, but you know, every variation you can think of easily has been done for weakening a bond and getting it to migrate and push out a leaving group. Okay, let's talk about E1 and E2 eliminations. You should already know E1 and E2 eliminations. When we teach organic chemistry at an introductory level here at UC Irvine and in most institutions, first things you learn about are SN1, SN2, E1, and E2. So we're going to talk about this to make sure we understand what's going on with elimination processes. So we'll talk about about elimination processes. You should all know that in an E2 elimination, you've got some sort of a proton beta to a leaving group, and a base comes in and then pulls the proton off. And this is just like other things that we've seen here. So in these cases, right, as the base comes in and attacks, it weakens this bond, and that weakened, more nucleophilic bond donates over into sigma star and pushes out the leaving group. Right? You didn't talk about it with sigma and sigma star when you took sophomore organic chemistry, but that's what was happening. You should have also seen reactions of carbocations, carbenium ions, where there was an empty p orbital, desperate for some pair of electrons. And so all you needed to do is come over here with some weak conjugate base, like under acidic conditions, and gently pull that proton off, and those electrons move right over and generate a CC double bond. Now the last mechanism, they waited until the very end of the quarter to teach you about, or the very end of the academic year, when they started talking about aldol processes. And then they finally fessed up and told you, oh yeah, there's this other mechanism called the E1 conjugate base, where a carbanion lone pair can just push out some leaving group. And it can be a crappy leaving group, like hydroxide anion. And that's the most common elimination mechanism. The one they waited till the end of the year to teach you about is the one that you should have learned about first. Let's go ahead and talk about these three different elimination pathways, mainly in the context of forming carbon-carbon bonds, but you could form other types of bonds. You'd use the same language, E1, E2, even if you're forming C double bond O or N double bond O or some other double bond. You usually don't get stable double bonds below the second row, right? Stable double bonds to sulfur or selenium or tin, those pi bonds are not stable. So it's second row atoms, C double bond C, C double bond N, C double bond O. That's what makes second row atoms special. Okay, so I mentioned already that the E1 conjugate base elimination mechanism is usually first introduced when you talk about aldol processes at the end of the year here. It's in our typical course. And so let's go ahead and draw out a partial mechanism for the aldol reaction, the aldol condensation reaction. You should have done this reaction in the labs here, an aldol condensation, if you took the chemistry 51C laboratory sequence. I'm not going to draw all the initial steps out, but you might remember that in an aldol reaction, you deprotonate, if you're just using sodium hydroxide, to make a teeny tiny amount of the enolate species. And the enolate species is nucleophilic. Here's one possible resonance structure for the enolate, and that makes a CC bond. Right? This is the way we make CC bonds in modern organic synthesis. This is the way you make CC bonds in nature. Every single lipid in your C18 lipids is made through this carbon-carbon bond forming process. We use aldol reactions, not Grignard reactions in nature. So I'm not going to show you all the proton transfers in this aldol process, so I'll just write the word aldol here. If you don't remember that, you can go look up that bond-forming process. But the intermediate that you get in an aldol reaction is an alcohol. Here's the alcohol. There we go. I'm not showing you, you have to protonate the O- in another step, but that's the intermediate you get. And under these conditions, sodium hydroxide, just slight heating here, to make the reaction a little faster, what's happening is kind of the same thing that happened in step 1. The first step of an aldol process is that you deprotonate alpha to a carbonyl. Those positions are acidic. They have pKs on the order of about 20 for a ketone, CH, next to a carbonyl. And so if it was easy to pull a proton off in step 1, it should still be easy to pull a proton off here. It's just as acidic as it was in the original starting material. So if you liked deprotonation in step 1, you have to like deprotonation here. So let's go ahead and pull the proton off. And so the issue is, why is that proton so acidic? The reason that proton is so acidic is because you can donate the electrons into the carbonyl. I'm going to draw an arrow pushing mechanism where I just leave the lone pair here on that carbon, but you could push the electrons all the way into the carbonyl and end up with an O-. So here when I draw it like this, right, I can easily see this nucleophilic carbanion. It's a CH atom or CH group with a negative charge and a lone pair. And now that I've got this carbanion lone pair there, it's kind of easy to see how that's going to push out a leaving group. And hydroxide is not a good leaving group for SN2. You would never, ever push out an alkoxide or a hydroxide group using a simple SN2 reaction. But this is not SN2. We've got a full-on carbanion. That carbanion is right here, is donating into that antibonding orbital, and it is pushing out that leaving group, and it goes away. That's an E1 conjugate base mechanism. This species right here is called the conjugate base. And so these reactions work well when you have something you can easily deprotonate to make a carbanion. Whoops, that's when they work well, when you can make a conjugate base by deprotonating something. To make an anion, usually a carbanion, but also O-. You could deprotonate to make O- and it would push out a leaving group, or N-. If you can deprotonate something and make an anionic lone pair or anionic pi system, you can push out a leaving group. Now, this sounds so obvious. How could anybody make a mistake here? But I promise you, you're going to do this. You're going to say, oh yeah, proton leaving group, E2 elimination. No, never, not ever would you do a one-step E2 elimination. It's a two-step E1 conjugate base elimination mechanism, right? This is what we've been talking about this whole quarter. Would you rather donate into sigma star for a CO or a pi star for a CO? I'd rather donate into a pi star for a CO. And so would so would these electrons, CO, right? This is what you want to do. Yes. Make the enolate and then use the enolate to push out the OH. Step 1 is you deprotonate and make the enolate. You don't directly push out the OH as you deprotonate. Don't try to do it in one step. It's never a single step mechanism. It always involves making an enolate species that then pushes out the leaving group. E2, one-step E2 eliminations are not easy. Those aren't easy. Okay, you've seen plenty of examples of E1 conjugate base. You're going to see a lot more examples of E1 conjugate base. We might not be using the phrase E1 conjugate base while we're pushing the arrows. Here's one example we've already seen. Somehow in discussion section, people found the mechanism for forming mesolates in the presence of triethylamine. I didn't expect you guys to know this mechanism, but since people put it on the board, what was the first step in that mechanism? This was an E1 conjugate base type mechanism. You had a mesyl chloride, and when you use triethylamine with mesyl chloride, not pyridine, but triethylamine, 100,000 times stronger than pyridine. When you use triethylamine with mesyl chloride, who would have guessed? You couldn't have guessed this, but somebody did a mechanistic study to show that you're deprotonating initially in order to make this conjugate base. That's what happens when you take mesyl chloride and triethylamine. You make this methane sulfonyl anion, carbanion stabilized by that sulfonyl group. And then in a second step, you push out the leaving group. Let's push out the leaving group. The leaving group is chloride, and you get this sulfene intermediate. That's an E1CB elimination mechanism, right? It's not a CC double bond, but it's the same sequence of steps. Deprotonate to make some sort of a stabilized anion, and then that anion can push out the leaving group. Let me show you another example. I don't think we certainly didn't cover this bottom example below in this class, but it's a common transformation. Quite often in organic chemistry, we use protecting groups. You should have learned about protecting groups in your introductory organic chemistry course, right? If you're trying to do lots of chemistry on one part of the molecule, like here, suppose you wanted to do some sort of chemistry here, but you didn't want the lone pairs on this nitrogen to get involved, you would have to protect that nitrogen to tone down the reactivity of that NH. So we commonly use carbonyl protecting groups that kind of suck the life out of these lone pairs so that you can't easily protonate the lone pairs. You can't use those lone pairs as nucleophiles because those lone pairs are already donating into the carbonyl. So it protects the nitrogen lone pairs from doing anything. But once you're done fiddling around with the rest of your molecule, you want to remove this protecting group and get it off of there. And so how do you get this protecting group off? This is called an FMOC protecting group, fluorenyl methoxycarbonyl, fluorenyl methyl oxycarbonyl, fluorenyl methoxycarbonyl, FMOC protecting group. I'm not sure if I got all the phrasing exactly right there. But when you want to remove an FMOC protecting group, here's the most typical conditions that you would use in the laboratory. You would use piperidine, and you'd use DMF. The DMF is not so consequential for you. You use a lot of piperidine. It's like half your solvent is piperidine. We've seen piperidine before in Novanagle condensations. It's not just a random choice. Triethylamine would not work here. You need piperidine for this. It kind of suggests it's going to act as a nucleophile somewhere in the reaction mechanism. Let's go and watch what's happening here. No way in the world you could have guessed this. But this CH that's right here, that's acidic enough to be deprotonated by piperidine at reasonable rates. Not low concentrations of piperidine, but at high concentrations of piperidine, you can pull that proton off. Let's go ahead and do that. Let's go ahead and draw what would happen if you're stirring this around in piperidine as a co-solvent. You would get a tiny amount of this deprotonated carbanion. Let me draw the lone pairs right there. Big red lone pairs. So you'll have a tiny amount of this fluorenyl anion. This tricyclic system is called fluorine. Let me just go ahead and write it out. Like, where does the word fluorine come from? Fluorine looks like this, and it's that 3-ring system with the 6-5-6 ring system. That's a fluorine ring system. And this carbanion is stable. Why is that such a stable carbanion? It's not easy. You can't just deprotonate butane. Right? We don't have any base that can deprotonate butane or simple. So one rationale for why this is so acidic is this is now an aromatic ring. There's 6 electrons in that central ring. So that helps to give this some stability here. And you'll hear other arguments for why that's so acidic, but that's a good rationale for you to keep in mind. And once you make that carbanion, we're set up for an E1CB elimination mechanism. You have a carbanion, you have a leaving group right next door. Let's go ahead and push that out. Goodbye. There we go. And so now we've pushed out this, this carbamate anion type species here. And remember from step 1, we still have this conjugate acid floating around like this. And so we're going to need to get that carbonyl off the nitrogen. How do we do that? We still have this B. I'll draw it out as B plus H because I wrote neutral B in the very beginning. So let me draw B plus H. I've got the conjugate acid, and I've got this anionic species, and so now we need to protonate it somehow to get rid of that group, the carbonyl group. Probably every cell in your body wants to protonate that O minus. Feel free to protonate the O minus. Does that make sense? That's happening. But it will not explain how you lose the carbonyl group. After you spend an hour trying to figure out how you're going to get rid of the CO2 by protonating O minus, you'll give up and take it back off, and you'll realize, oh, you know what? I really have to protonate the nitrogen. You're not crazy for trying to protonate the O minus. That's, well, what am I doing there? Not the B. There we go. You're not crazy for wanting to protonate the O minus. That's perfectly natural, but you're never going to lose CO2 if you protonate the O minus. What you need to do is every once in a while, one of these molecules will pick up a proton on nitrogen. And now you are perfectly set up to blow out carbon dioxide. Because what will happen is these lone pairs right here on this oxygen are anti-paraplanar to this NC bond. They're bending over. You need that O minus. You're weakening that CN bond. And because you've weakened that CN bond and it's got a positive charge, it's easy to break it and give the electrons right to the nitrogen. And so the byproducts in this reaction are carbon dioxide, which will bubble right out of your reaction mixture, and your free amine. And now that free amine has its own lone pair there, totally free and easy to start doing nucleophilic chemistry in your next 10 synthesis steps that you want to do. Now that amine's ready for you to start doing chemistry with that and isolate that free amine. Now, why did they use piperidine? You couldn't have guessed this part. Somebody figured out that piperidine helps get rid of this reactive fluorine. The piperidine adds back in to make that same aromatic fluorenyl anion, and then you protonate here. There's some proton transfers. But that's the byproduct that you just wash away when you're done with the reaction. So this is an E1CB elimination mechanism. Reaction works great with tetrabutylammonium fluoride. F- is also good as piperidine, except you don't need as much. But you make a carbanion, and it pushes out a leaving group.